We're going to look at complex numbers in polar form. We're going to define a few things, and we're going to convert between Cartesian and polar and vice versa. First up, just like with some of our previous work on complex numbers, e.g. in Cartesian form when we have z equals a plus bi, there's a lot of parallels or corresponding elements, isomorphism with polar form and the 2D vectors. Okay, so there's a lot of correspondence, just like with this form. With polar form also, there's a lot of correspondence between the two-dimensional vectors. So let's have a look into that. If we've got some complex number z on the Argand plane, like this one here, we can look at it in a different way with different parameters. We can look at an angle, as we do with two-dimensional vectors in polar form. We can look at a length along there, which can be called r. And, of course, we have some sort of x plus yi or a plus bi. So, x plus yi. The x and y are going to figure in this. That's why I haven't used the a and the b, but it's the same. So for this Argand diagram, we have complex number z is x plus yi, and similarly, because of the right angle triangle involved, and just like with the trig that's involved in 2D vectors, we have components, and we also have a component horizontally as well, and that one would be called x, and this one would be called y. That's no big surprise, we have a right angle there. So from work to do with the unit circle, trigonometry, and two-dimensional vectors, x's are cos theta, so wrong colour, r cos theta, so I'll just write that down there. Y is r sin theta, and it's got an I operator on it, so write it like that. R I should say, is a factor of both of those terms. Okay, so I could have put the r outside of here too, and so hence r is cos theta plus, you can move the I wherever you like as well, cos theta plus I sin theta. Now that is the basic form of a complex number in polar form. To abbreviate all that, we use the notation CIS, and that's cos I sin. So we've got r cis theta, which means cos theta plus I sin theta, which abbreviates what we have to write. So there we have it. That's the basic polar form. As with 2D complex numbers, we have r is able to be calculated using an application of Pythagoras' theorem. So r is x squared plus y squared. Now the name for r is the modulus. So the length of that line corresponds to the modulus. Okay. In vectors, we would use the word magnitude. Okay, so magnitude and modulus are pretty much the same thing. Certainly mathematically they are. Okay, they're just used in different topics in a slightly different manner, but essentially they're corresponding things. Just like with vectors, we can use this notation here. Okay, the magnitude notation, it's called the modulus of complex numbers, so that would be the same as the modulus of z. So the modulus of z is equal to the r on the diagram there. The theta on the diagram has a name, and it's called the argument. You might think that's amusing. The argument is a bit like the direction, and it is anti-clockwise. The direction of a vector, 2D vector, is corresponding to the argument in a complex number, and it is anti-clockwise too. And we use degrees and radians, but in this context we'll mainly use radians. So we've got the argument and it's anti-clockwise, as you saw in your unit circle and in polar form of 2D vectors. Now, polar form is often called mod arg form. And that's because we have modulus and argument. It's the modulus argument form, or mod arg for short. So you can call it mod arg form if you like, or modulus argument form, as well as polar form. So we have to make some changes to our Argand diagram if we want to plot these values of modulus and argument, and you can see that's what we have. That's how we change the Argand diagram when we're in mod arg or polar form. And looking at some of those examples plotted on there, you can see how it works. And basically we go out from the center and we go out the number of units that correspond with the modulus. And just look closely, because that is a very faint circle there. So each of these on this particular one represents a half, so 2 represents 1, 2 increments, so, and this would be 3 out here. And then you just follow that around radially. Okay, and the other thing you plot is the this one's in radians, anti-clockwise you plot the argument. And so this one here is in increments of pi on 12 radians, or 15 degrees. Okay, so 2 of them would make the pi on 6 you see there. Okay, now you'll notice that it doesn't go above pi, it starts to go negative, and we're going to talk about what's called the principal argument, because I'll go through the reasons, but the principal argument, or the principal value of the argument, sometimes that extra part of the phrase exists. The principal value of the argument, or just the principal argument, is basically when we have things, the convention to avoid issues is it can go up to pi, it can go down to, but not including negative pi, so the angle goes down there. So in other words, arg z is between negative pi, non-inclusive, and pi. Okay, we'll go through the reasons why. That's to do with the trigonometry in it. When we're looking at the cos and the sine involved, cos theta and sine theta have this issue of coterminality, and so you would have seen in your studies of trig that cos theta actually equals cos of theta plus 2 pi n, where n is any integer, so it's positive or negative, right? And sine corresponds to that as well. We have theta plus multiples of 2 pi if we're in radians. Okay, so that means that we have this coterminality. When we put it together in a complex number then, so z is r cis theta, but it's also r cis theta plus 2 pi n. Okay, so it's non-unique. Okay, there's a non-uniqueness need to be aware of. But if you understand your trigonometry from your unit circle, that shouldn't be a major surprise. Hence, we have a principal argument, or a principal value of the argument, and you can see that applied here in our radial diagram. Okay, now the final part of the video will deal with two types of conversions, and you need to be able to convert between polar form and Cartesian form. So at the start here we have two examples. They're both in Cartesian form. So that's x plus iy or yi, which is the same as a plus bi. So how do we convert them? Well, we know, we've looked at the beginning of this video. So we've got r equals the square root of x squared plus y squared. That comes out as 2. Now that's basically that's the modulus. Okay, so that's equal to you could also write that as that, the modulus. The argument now, probably with some complex numbers, you need to take a bit more care than others, but to find the arg of this, alright, sometimes it's very helpful to sketch it. Okay, so we have 1 plus root 3i. This one's fairly easy because it's in that first quadrant, and so this is no sweat really, this one. The second one might be. So 1 plus root 3i, so that's going to be no problem, and the argument will be that angle there. So it's a straight application of trigonometry. You could use sine or cos or tan, but I guess from your 2D vectors you'd be looking at tan. So tan of the angle, tan of arc z, so tan of theta. Alright, and looking at the complex number, we've got root 3 there, and we've got 1 there. So alright, from our complex number, and so tan theta is root 3 over 1, or just root 3. So theta is the inverse tan of root 3. We can do that quite straightforward. Inverse tan of root 3, because it's in that first quadrant. And tables of exact values are very handy to memorize to speed things up. Theta, the angle, the argument is pi on 3. So that's arg z. Arg z is pi on 3. Putting it together, we've got the complex number is 2 cis pi on 3, or in other words 2 cos pi on 3 I sine pi on 3. For the second one, 2 minus 2i, the modulus of z is quite straightforward, comes out as 2 root 2. Now draw this one because we have to look at the true argument for it, and basically we have 2 minus 2i, so that might be down there like that. Okay, and remember we're going to have to look at the principal argument once we get it close to the end. Okay, so I tend to do that bit last. Okay, I crunch first. So without considering the principal argument for a moment, anti-clockwise it's travelled around that angle there. Okay, so the argument has moved through there, for temporarily ignoring the principal argument. We'll get to that. Now doing a bit of straightforward trig, we've got just regular triangular trig. Just to get the size of that angle, we have 2 across there, and we have 2 down here. Okay, and we've got our right angle there. We do have 2 root 2 along the hypotenuse too, if we wish to put that in. So to find this acute angle in here, that acute angle in there, we can use tan. Okay, so just treating it as just a right angle triangle temporarily to get the magnitude of that little angle there, we've got tan of theta equals 2 over 2, or 1. In radians, theta would be equal to pi on 4 radians. So it's moved through an argument of 7 pi on 4, but because the preference is for the principal argument, it's simply just the case, because we've got to stick between negative pi and pi. Basically, argz is negative pi and 4. We just go clockwise by pi and 4 and we will get where that complex number is. So we have our complex number z equals 2 root 2 cis negative pi on 4 using the principal argument. Always draw a diagram. Finally, now we're going to convert this polar form complex number into Cartesian form, and we have 2 cis negative 2 pi on 3. Alright, and you don't need to write this, but you do know that it's cos negative 2 pi on 3 plus I sine negative 2 pi over 3. Okay, so we basically have, in polar form, we have 2. Now it's gone in clockwise direction by 2 pi and 3 radians, so it's around there. So that's 2 pi on 3 going in a clockwise manner. Okay, so R equals, we've got to find R. R is 2, and argz is negative 2 pi and 3. We've identified those. So, because we're not using inverse trig, it is a straightforward manner now that we just go, sorry, I should say R cos theta and R sin theta. Let me fix that. And it's a case of subbing in. And we can check the reasonableness of our answer in case we are doubting it. I'll do that in a minute. So we can just enter that straight into a calculator. Okay, and likewise for y, we have 2 sine negative 2 pi over 3. Make sure you're in radians mode. Enter it in. And we get negative 1 and negative root 3 for our answers. So that were the values of x and y. So we've got x plus iy, so therefore we have negative 1 minus root 3 I for our complex number in Cartesian form. And look, if you're wondering, going, oh, I wonder if the calculator gave me the answer. When you're subbing it in and not doing inverse trig, it is quite reliable, but you can check it because, well, that answer, does that relate to the diagram we drew? So does that look about right? Negative 1 in that direction and negative root 3, which is about negative 1.7 that way. So that'd be to the left and down. And yeah, so that seems pretty reasonable.